some of the definitions like drift velocity, conductivity, and current density, resistivity, resistance, and everything. I will go through some of the topics today, like what is intrinsic semiconductor and what is p-type semiconductor and what is n-type semiconductor. What are the difference, like how the conductivity changes compared to p-type and n-type, and with respect to intrinsic semiconductor, everything we will see. What is the contribution of which charge carriers is contributing to produce the current? Everything we will go through today, and we will solve some of the problems related to the topic that we have seen so far, including drift velocity, conductivity, and everything. Okay, today the first topic is intrinsic semiconductor. Intrinsic semiconductor is like a pure semiconductor. We won't look any any additional charge carriers. For example, if we have a pure silicon, intrinsic semiconductor means it may be germanium or silicon. I'm assuming it to be silicon. Let's talk about at two different temperatures. One is at 0 kelvins, another one is at 300 degree Kelvin. In this particular temperature, this is the conduction band and this is the valency band, and electrons are there initially at the valency band. By applying some potential, the electron will move from valency band to conduction band, and that produces, and then electron will move in the conduction band, and that gives rise to the current will flow. But at this particular temperature range, 0 kelvins, we are not applying any devices, any additional electric field, which is nothing but voltage, to move electron from valency band to conduction band. All the electrons will lie only at this particular, energy levels only, in the valency band only. Electron cannot move from valency band to conduction band. Because of this reason, there is no electrons in the valency conduction band, and there is no holes present in the valency band, which is a main reason there is zero current at this particular temperature. I hope this is clear. I want to make one point here, is that whatever the electrons lie within a conduction band, those are the charge carriers to produce current, as well as the holes present in the valency band. These are the two charge carriers will produce current. What I mean to say is definition as what I mean to say is current. We all know the current, and that current is having two types. One is from electron current, another one is hole current, which is nothing but the total current. In this particular case, electron current, what I mean to say is electrons present in the conduction band will give the electron current. If, for example, this is the conduction band, and the electrons present in the conduction band will produce the electron current. In the same way, the holes present in the valency band will give you the hole current, and by summing those two, we will get a current, total current. But there is one more thing, the mobility. What I have told last class, mobility is nothing but how much speed that an electron or a hole move from one place to another place. The drift velocity of the electron is very high compared to the hole. Hole will move very slowly. The electron can move very fast, even sometimes double the speed. That is the reason the hole current is comparative to electron current is much higher than the hole current. But in this particular condition, at 0 kelvins, there is no current and that current is 0. But at 300 kelvins, I am saying, let's say at 300 kelvins, let us assume 300 kelvins. This particular temperature is more than enough for an electron, not for all the electrons, but some electrons can move from from valency band to conduction band. I repeat, at 0 kelvins, no electron will move from valency band to conduction band. That is the reason we won't get any additional current, not additional, there is no current at all in the intrinsic semiconductor at 0 kelvins. At 300 kelvins, some of the electrons can move from valency band to conduction band. Because of the electron count is very less, the current is very small, maybe in terms of milliamperes, 1 milliampere, sometimes it may be 0.1 milliamperes in practical as well. And 0.1 milliamperes is not enough for any of the electronic device to operate. I mean, it is not that much sufficient. Electron, this much current is not sufficient to work an electronic device. We need to do something to increase the electron count, which will automatically increase the current magnitude. That means if we are getting 1 milliamperes, this is not sufficient. We want something called, let's say, 1 ampere current. Oh, yeah, 1 ampere current. You can see 10 to the power of 3 is the magnitude difference compared to these two, and we need to increase that much magnitude of current. And that is possible using a method called doping, and which uses n-type and p-type semiconductor, depends on the doping of atoms. Here we see in the intrinsic semiconductor, the total number of electron concentration and hole concentration is same. It is because the amount of electrons, the number of electrons moving from valency band to conduction band leaves a hole in the valency band. For example, there are let's say 10 electrons in the valency band initially. Now the first electron moves from here to here. Okay, leaves one hole here and one electron in the conduction band, one hole in the valency band. Both are same. And this process is not in a number of tens, but in the number of 10 to the power of 10 and 10 to the power of 12. You can imagine the number. Every time a hole moving from valency band to conduction band, it leaves a hole. And that is the reason why electron concentration is exactly equal to the hole concentration. There is no other any other process which increases the electron count in the valency band nor hole concentration in the valency band. I mean, electron count in the conduction band and hole concentration in the valency band. And this point is valid at 300 kelvins, because at 0 kelvins, let us assume at 0 kelvins, the electron cannot move from here to here, and there is no electrons present in the conduction band. That means electron count is 0 at 0 kelvins. If electrons is 0, and obviously hole concentration is also 0. N is the electron concentration and P is the hole concentration, and which is nothing but intrinsic concentration. This is very very important, and make sure the notation is very clear. N suffix I, intrinsic concentration, and in most of the problems they will give directly Ni, and which is nothing but intrinsic semiconductor concentration, and this is constant it is observed practically. It is 1.5 into 10 to the power of 10 per centimeter cube for silicon, and 2.5 into 10 to the power of 13 for germanium. Here one can easily observe that germanium has more, like in terms of 10 to the power of minus 3 order more compared to the silicon. But we will prefer only silicon because of its own advantage. We'll see in case of N-type and P-type semiconductor. This is one of the important definition I want to say. NP is equals to Ni square. This statement is valid for all. For any semiconductor, irrespective of its p-type or n-type or n-type, no matter what, this statement is valid. This statement says that if we have a semiconductor bar, it may be intrinsic, it may be n-type, it may be p-type. Here n is nothing but electron concentration, p is nothing but hole concentration, and which is nothing but Ni square. I mean, which is equals to Ni square. The Ni is intrinsic semiconductor concentration at 300 kelvins. For example, in this semiconductor bar, let's say N is electron concentration and P is a hole concentration. Make sure that always electron concentration is not equals to hole concentration. This statement is valid only for intrinsic semiconductor. But if we go for n-type semiconductor, where electron concentration is more compared to the hole concentration, in case of p-type semiconductor, hole concentration is more compared to the n-type semiconductor. Electron concentration. But irrespective of the semiconductor type, this statement is always valid. Maybe this is high or this is high, no matter what. But this product will always be true, which is equals to Ni square. Np is equals to Ni square. This is valid. Okay, we will see some of the problems on this, because this is a very very important concept where there is a maximum probability asking a question in the gate exam as well. We'll go through once. Here, Ni is given. Ni has to calculate by using some of the formula, and that can be calculated using this. But ideally, not ideally, but in the gate exam point of view, most of the times they will give the Ni directly, and they will ask you to find electron concentration or hole concentration, some of the parameter which can be depends on electron concentration or hole concentration, whatever. But there is a very less probability for asking a question on this particular question on Ni directly. But it is better to concentrate on this as well. And here you guys can see Ni square is equals to, this is a constant, this is a constant, and that constant value they will give directly in the exam, in the question. And they will give temperature. What is the temperature? That depends on. And exponential power, energy gap. Here you guys can see easily En naught. The not symbol is given because it is an intrinsic semiconductor. And that too, it is at 0 kelvins. What is the energy gap between those two? And KT. K is a Boltzmann constant and T is an Argand temperature in kelvins. Make sure guys, this is in temperature always, not always, most of the cases is temperature is in kelvins, not in degrees. They may give you in degrees, but you have to convert it into kelvins. Here one point has to clear that what is the depends on temperature. Here you guys may thought like it is directly depends on the temperature. I mean it may be a direct proportion, but that is not the case always, because there is a one more temperature factor which involves here, which is nothing but exponential term. The exponential term will have a huge value compared to the direct cube after a few like 500 kelvins or 600 kelvins or at that temperature ranges, it is very high, and this factor will dominate compared to this, and we will get a negative impact on NIA by increasing temperature, and the concentration will get decreased. What I mean to say is initially it will get increase the concentration. After a certain temperature, this exponential factor will dominate compared to this, and we will get a negative impact. At ideally speaking, the temperature, the electron concentration will become 0 at this point after a huge Kelvin, like 1500 kelvins or 1600 kelvins. It is ideally possible, but practically speaking, it is not the case. Concentration will not get 0 once it get increases, but ideally this is the case. And yeah. Now connectivity. We have seen definition of connectivity in the last class. We will go through it once again. It is same n q mu n, p q mu p. These two factors involves in the conductivity, where n is electron concentration and p is hole concentration. Q is charge of an electron, Q, and mu n and mu p are mobilities. That means conductivity of electrons. This is the contribution of conductivity of electrons, and this is the contribution of concentration of holes. In the intrinsic semiconductor, N and P both are equal. There is more or less same impact on both the factors on conductivity. We cannot neglect one of the factor in case of intrinsic semiconductor. We cannot neglect P or we cannot neglect N. Both will contribute, not same, but relatively same, at least by some order it will produce an equal current. So both of terms are equally important. So by the definition of intrinsic semiconductor, we know N and P are equal, and that is equals to the intrinsic semiconductor concentration, which is nothing but Ni. By replacing in the formula here, we can take Ni, intrinsic semiconductor concentration, and Q out of the equation, and there is something called mobility count which has to sum. and this is the formula for conductivity in case of intrinsic semiconductor. But my suggestion is that don't summarize all the formulas. Instead, remember this one, and based on the type on the given parameters, one can be neglected. I mean, one term will get neglected sometimes. If it is intrinsic, both has to some, and we can calculate conductivity very easily. This is all about connectivity in an intrinsic semiconductor. Now we need to look at one more important topic called charge density. This is valid in any semiconductor, irrespective of the type, and just like this formula, NP, electron concentration into hole concentration, is equals to Ni square. In the same way, this is same. This is valid. That means if we have a semiconductor bar, if we have a semiconductor bar, like this, the hole concentration and the electron concentration and the donor concentration ND. I will talk this in a few minutes, but just keep it in mind. There is one term called donor concentration and acceptor concentration. NA. Donor, D for donor, A for acceptor, and N is a concentration notation, but this is intrinsic parameters, and this is a doping parameters. We'll see in few minutes, but just keep it in mind. And both the charges are same. What is charge density? Means the charges is equal, meaning the total positive charge present in a semiconductor and total negative charge present in a semiconductor, both are same. Which means, as we all are know, that electron is a negatively has a negative, you know, what I can say, negative charge, right? And hole is a positive charge, E positive. This is the hole and this is the electron. And coming to these donor charges and ND, if for if it donates something, then it will get a positive. I mean, they are giving something, so ND is comes under positive charge. And acceptor, if something is accepting, then which is nothing but N A minus. This is accepting, so that is the reason why it has a negative charge, and it is giving something, so it has a positive charge. And by summation, these two are equal. Are equal. From this particular definition only, the intrinsic semiconductor definition comes into picture. Like, we don't have a ND or NA in case of intrinsic semiconductor, both will get 0. If both are 0, then P is equals to N, which is nothing but an intrinsic semiconductor definition. Okay, I think this part is clear, and if you guys need any topic to revise once again, and please let me know. If not, we can jump into p-type semiconductor, and we will learn details about the p-type semiconductor. I'll give you a minute, just think about it, just go through the document. If you guys have any questions, please let me know. You guys can unmute yourself, or you guys can message on the chat box. Yeah, fine. I didn't get any message or question from your side. I hope everyone understood the concept. Now we will jump to p-type semiconductor. p-type semiconductor. What is a p-type semiconductor? Uh, wait, will- okay, okay, we'll start. We have this is a do not concern. This is a conduction band. Let me just start. Okay, this is a conduction band, and this is the valency band. What we have seen in case of intrinsic semiconductors, the electrons will move from here to here, and there will be electrons in the conduction band and holes in the valency band, which produces current at 300 degree kelvins, or even sometimes not always true, but 250 kelvins is also enough sometimes that electron can excite from valency band to conduction band and leads to current flow. But in this particular condition, we are doping additional things like we have an acceptor concentration, acceptor energy level. In case of intrinsic semiconductor, we have two energy levels. One is conduction band, another one is a valency band. Electron can either lie in valency band, I mean below the valency band, or above the conduction band, but this is a forbidden band, and electron cannot lie within this particular range. I mean, I'm talking about this range in case of intrinsic semiconductor. But here there is three different levels. One is conduction band, another one is valency band, one more thing called acceptor level. That particular acceptor level has holes. I mean, holes is nothing but lack of electrons. So here there are electrons still at 0 kelvins, let us assume. Electron doesn't have any additional voltage or any energy to move from here to here, I mean from valency band to conduction band, as well as valency band to the acceptor level, because there is a hole and the electron can lie in the acceptor level as well, but electron cannot jump even this small barrier. Very few, like if it is 100 and it is 2 or 3 factors, even though it is very small, without a volt energy, electron cannot move, and that is the case at 0 kelvins. At 0 kelvins, electron doesn't have enough energy to move, to cross this small barrier, and it cannot move. Let us assume at 50 kelvins. 50 kelvins. What happens at 50 kelvins is electrons have some energy. It has some energy. It can cross this barrier, this small barrier. But keep it in mind, in this case also, the electron cannot move from valency band to conduction band, but it can move from the acceptor level, I mean from valency band to acceptor level. Obviously, here the electron will present. By moving an electron from valency band to acceptor level, it will release a hole, and it has a hole. you can see guys, the electrons here is 0 still. Holes count get increased. But this is not the case in intrinsic semiconductor. Intrinsic semiconductor, the electron and hole concentration are both are same, but in this particular case, that is not the story. This is completely a different thing. So this I have explained only with one electron and one simple process, but the process will continue for a, process will continue for a many electrons. So the large count of electrons can move from here to here, and every single time it moves from valency band to acceptor level, it releases holes, but still the electrons in here is 0. Even if it reaches 250 kelvins, then there are two possibilities. Electrons can directly jump. Let me take a different color. Spotting, yeah, matte. There are two conditions at 250 degrees kelvins. Let's talk about 250 kelvins in the red ink. The electrons present in the acceptor level can move from conduction band. That is one possibility. Or electron can directly jump from here to here. This is another possibility. But if electron is moving from here to here, there is a hole. And this particular case, the electron is moved from Na to conduction band. Now there is a hole again. Now this electron can easily move. And this process continues every single time. And that is the reason why this statement comes into picture. Hole concentration in the valency band and electron concentration in the conduction band, the relationship between them. And obviously one can say using this particular process, hole concentration is huge compared to the electron concentration. Every single time I'm talking about hole concentration, it does mean that I'm talking about electron concentration in the valency band only, not in the conduction band. There is nothing like hole in the conduction band. And there is no use electron present in the valency band. And so every time I'm talking about electron concentration, it does mean only that the electron is present in the conduction band, not in the valence band. Okay. I hope this process is clear. This is a very fundamental, and it is a foundation for entire electronic story. So make sure that this concept is clear. If this is clear, and I will move to next concept. Here P and N is nothing but electron hole and electron concentration respectively. Obviously the hole concentration is very high, so we'll have a relationship much greater than the electron concentration. If by just considering these two definitions, I mean this simple relationship, we can derive an important formula, that is charge density. As we have seen that positive charges and is equal to the negative charge present in a semiconductor ball. And Na plus N, that means acceptor concentration plus the electron concentration is equals to donor concentration plus hole concentration. We don't have any donor level in this case as well. In case of intrinsic semiconductor, Na and Nd both are 0, so we have a relationship P is equals to N. But in this condition, we have an acceptor level. So we should not make it 0. And there is a relationship Na plus N is equal to P. And this is ideal case I'm talking about. But in practical, we know P is very high compared to the N, so we can make it intentionally zero, not ideally zero. Intentionally zero does mean that we are approximating something. So that is the reason NA is approximately equals to the P. Approximately equals to the P. Okay. Now, if these 2 points are clear, and I will move forward and I will say this important relationship within semiconductor bar, electron concentration and hole concentration is equal to Ni square. We know that we know the hole concentration from this Na. We can find out, we can identify the hole concentration from this particular equation, that electron concentration is equals to the Ni square divided by hole concentration, and hole concentration is equals to Na. What I mean to say is, in majority of the cases, we will use this particular formula to identify the minority charge carriers. What is meant by minority charge carriers? In a semiconductor bar, if I am talking about p-type semiconductor where hole count is higher compared to the electron concentration, so the majority charge carriers is holes and minority charge carriers are electrons. So every time we will use, not every time, but most of the cases we will use this formula just to find minority charge carriers. In the p-type, it is electron concentration by using a hole concentration. Okay. Now we'll move it forward and we will find conductivity. We know this basic definition from a conductivity, which is nothing but NQ mu N PQ mu P. But in this particular case, we have an approximate. As we have seen in case of intrinsic semiconductor, we don't have any approximate. We don't have any approximate, and we have to substitute both the electron concentration and hole concentration, and we have to find the conductivity. But in case of p-type semiconductor, we have a majority charge carriers as holes, so we can approximate and we can intentionally make it zero. I mean electron concentration, and the holes is a majority charge carriers, and which is a mainly contribution for conductivity. If the in a p-type semiconductor I'm talking about, by this equation we can see by using this formula we can see that there is no term called N here, I mean hole concentration, which is nothing but every time the current produced in the p-type is mainly due to holes, not because of electrons. Not because of electrons, and it is only because of holes. And one can approximate a bit further, and we can substitute Na in place of P, and we'll get this formula. If you guys know this entire story behind the p-type semiconductor, then remembering all these formulas are not needed, and you can directly proceed at the time of the problem solvation only. Okay, but we will solve some of the problems on these as well, so that you guys can get a better idea how to deal in the exam. I hope this is clear. If you guys are clear in this particular semiconductor type, then N type is pretty simple and the same process continues. But I will explain. We have, in this case also, we have a conduction band and valency band. In this case, we have a donor. We have a donor, and this donor can donate electrons even at the lesser temperature. Let's say we are observing for 3 different temperatures. Uh, let's say at 0 kelvins. What is the process at 0 kelvins? The electrons are present here as well as here. Okay. The electrons are present here as well as here, and at 0 kelvins, the electron cannot move either from here to here or from here to here. There is no chance at all. And electron, there is no way to move, and still there is 0 electrons present in the conduction band at 0 kelvins. Okay, let us assume at 50 kelvins. In this case, these electrons cannot move from here to here to here, but these electrons can easily move because the energy gap between these two is very small, and it can easily move with a less energy. The same thing observed in case of p type, but there the electron move from one here to acceptor level, but these electrons will move to conduction band. Okay. Similarly, if you guys observe at 300 kelvins, and the same story repeats, but in this case, the electron can jump from here to here or here to here as well. But in most cases, the electron will jump from here to here only, and then electron jump from here to here. You know, the majority charge, the electrons present in the conduction band is because of this donors only, not because of this valence electrons in the valence band. So we have a definition that electron concentration is high compared to the hole concentration, and the same charge density Na and then Na plus N is equals to Nd plus P. In this case, we don't have any acceptor, so we can neglect this part. This is ideally 0, and then we have a donor level, but here we are making first approximation, that is P is approximately 0. If P is approximately 0, then we will get approximation N is equals to Nd, which is nothing but the electrons present in the conduction band is mainly due to the donor atoms present in the donor level, not from the valency band. This is the meaning of this particular formula. And if you guys substitute this particular formula in the here, Np is equal to Ni square. I already talked about this formula that it is mainly used to find the minority charge carrier concentration. In this case, it is P, which is nothing but holes. Ni square is equals Ni square by N. N is nothing but majority charge carriers, and it is approximately equals to, not exactly equals, it is nothing but Nd, donor concentration. Similarly, one can find out the conductivity from this formula Nq mu n plus Pq mu p, and p is very small, so we can make it 0, and we'll get Nq mu n. Nq mu n, yes. This is all about, guys, n-type and p-type semiconductor, how n-type is formed and p-type is formed, and what is the reason behind that, and everything I have talked. If you guys have any questions, please rise in the chat box, or you can unmute yourself. Okay, if you guys are clear with the concept, then we will take short break this moment, and we will continue it at 5 o'clock exactly. And I will share the new Zoom link in the group within a minute. You guys can join at 5 o'clock. Okay, the class will get resumed at the time. Okay, from 5 to 5:40. We will go through some of the formal questions. These are the important questions that I have observed, like which covers every single concept to solve these problems. We will solve this problem so that, and at this moment only, I will try to introduce the concepts again. Not introduce. I will make concepts much more clear at the time. Okay, you guys can take break for 10 minutes and we will join at the 5 o'clock again.